Hello everyone, this is Sumit Patil here, and this is an overview lecture on the academic paper training language models to follow instructions with human feedback. This is a part of paper reading task given in natural language understanding course. So LLMs nowadays have become an integral part of our day-to-day activities where we use LLMs almost for all from very simple tasks to complex tasks. Simple tasks would be as simple as scheduling a meeting or um, getting the optimal timeline for a particular day to complex tasks such as understanding a particular concept or an academic paper itself. But it was not the same 4 years ago. For earlier LLMs, even though were trained on good amount of data, huge amount of data, and they were able to predict the next token very much rightly, but they lacked understanding of human intent. LLMs are were meant to understand the humans user's intention both implicitly and explicitly stated and perform their tasks to achieve the humans goals and align themselves with the preferences of humans. But this was not happening because LLM, the training objective of LLM was to simply predict the next token given the previous sequence of tokens and the input prompt, but and thus the requirement of matching human users intention was never a part of the training objective. Thus LLMs never were trained for that purpose. For example, given a prompt to GPT-3 which was untuned, such that it has to explain gravity to a 10-year-old kid and also be brief, it simply generates two statements which are very vague and are not very much related to gravity as we expect it to be. However, if the same prompt was given to an Instruct GPT model, it did give a longer response than the GPT-3 model, but it included both scientific and rea- let's say metaphorical explanation to gravity, thus helping the student understand better. Now, this is an issue that this issue raised because the LLMs were not aligned with human preferences. Now, alignment was not very clearly understood until this paper was released. There were many multiple definitions of alignments in the community, but not a fixed framework. Thus, this paper proposes a 3H framework for alignment, which includes helpfulness, honesty, and harmlessness. Coming to helpfulness, the LLMs must ensure that not the LLMs, we must ensure that the LLMs are trained um, rightly to generate responses that are very helpful to the user, helping them to complete the task rather than simply generating a response and not being rational about the response. So the LLMs must be able to understand the implicit intent as well as the explicit intent that instructions that the user gives, and also help them solve their task and not just respond by giving a verbose answer. For example, if I ask to fix a particular code of mine, I do not need the complete fix to the code, but also I would want to what you call and neither do I just want to know what is wrong in the code. I want both. That is, I want to understand what is wrong with my code, but also I need to understand what fix will do the task. Coming to honesty, LLMs were known for hallucinating and meaning producing facts that are not actually true and stating them with a lot of confidence. But this is something that is not right, as honesty is a foundation of human principles as well. That is the reason we want LLMs to be honest. If they are not sure of a particular topic, they should explicitly state that they're not sure rather than simply generating a response. Coming to the third and a critical uh, edge, which is harmlessness. Because LLMs are trained on real world data and real world data is inherently biased, we would want we would want our LLMs to not be biased and be inclusive of the entire society in which we live in. Thus, the LLMs should not cause any physical, psychological, or social harm. They must not generate any toxic response even though they are explicitly asked to generate a toxic response. For example, if an LLM is asked to give a plan for a terror attack, the LLM should explicitly state that it will not cater to the request rather than generating a response while also giving precautious let's say, while also giving precautions to it. Giving the precautions is not is not what is needed, but not generating a response is something that will be better. Now this paper proposes a three-step pipeline to address the issue of uh, alignment. The first step is supervised fine tuning, where the baseline LLM that we have is fine tuned on a prompt responses pairs, prompt response pair, where response are actually, let's say, generated by humans, uh, which are actually preferred by humans for a given prompt. We'll talk more about supervised fine tuning a little later. Coming to the second step is reward modeling. Now, uh, we need a quantitative estimation of which response is better for a given prompt and which is not. Thus, we train a particular model to score a response given the prompt and which are actually based on the human preferences. Thus, the score will be higher to the responses which are close to what human expects and lower to the one that is not what is preferred by humans. Coming to the third and final step is RL fine tuning, where we use PPO to change the policies of LLMs to answer better to a particular prompt. Coming to supervised fine tuning, now we, the dataset for this step was prepared by using two main sources. One is the OpenAI's Playground API, where for a given prompt, users submitted the ideal response that they would want for this particular prompt. And second is manual entries, where OpenAI hired people to write ideal responses from scratch for a particular prompt. Now, given this data set, they fine-tuned the LLM to generate these responses, and the specifications of their training are given in the slide. However, one important before going further, the prompts actually included different variety, which is a plain prompt where an arbitrary task was given, few short uh, method or few short learning was also included, where the LLMs were given instructions and then multiple queries were asked and multiple responses were expected based on that instruction. And the third one is user based response, where it is related to users personal requests. However, we could not stop at supervised fine tuning because the data that is used to train the LLMs is quite low and is generated by a given set of people. But humanity is much larger than the subset of people. Thus, uh, we cannot, let's say, generalize to we cannot ensure that we have trained the LLM to on all entire prompt distribution. Second limitation is generalization. Since we cannot cover all types of topics in our LLM, in our supervised fine tuning, sorry, so we will not be able to generalize, the LLM will not be able to generalize generating better responses to something that is outside the given topic. In fact, the supervised fine-tuned LLM may even perform worse than the baseline LLM on topics that are that are outside the fine-tuning dataset. Third thing is it is not instruction fine-tuned yet, so the LLMs are still not able to follow the user's intent. And fourth thing is the bias, since the community which is the subset of people that is used to generate the data set for fine tuning this LLM could have a particular bias towards some entity. Thus, the LLM also gets fine tuned to have the bias to that entity. Now, that is the reason we come to second step, which is reward modeling. So we train a model to generate a score or give a score for a particular response for a particular prompt. Now, while doing the training, we to avoid biases and uh, to have computational efficiency, a subset of responses were given to humans, and they were asked to rank these responses for the given prompt. Since generating ideal responses a little tougher than ranking responses generated by multiple LLMs, that was the method used to create data set for this reward modeling, and the model and the model was trained. The loss function we can see here is as explained in the lecture classes that we had. Now, important things to note here is we have a pair of responses where YW indicates winning response, that is a good response, and YL indicates a losing response or a bad response to a particular prompt. Thus, we want to maximize the difference between the score for a winning response and the score for a losing response, so that the sigma we want to maximize this difference so that sigma of a high number would be 1 and log of that would be 0. Thus the loss would be as low as possible if the winning response score and the losing response score are as far as possible. Now this is the loss function on which the reward model are trained, and then we freeze the weights of reward model. Once the reward model's weights are freezed, we go to fine tuning our LLM using reinforcement learning with PPO. PPO is proximal policy optimization, where we try to ensure that our LLM is fine tuned to maximize the reward, but also to be very close to the baseline supervised fine tuned model. Now the reason for now we obviously know that we want to maximize our LLM's our reward to a particular response for a given prompt, but the reason for including this term in the loss function is to ensure that there is no reward hacking that is happening, meaning that it could be possible that to maximize reward, LLMs simply start generating responses that have higher reward, but the response is nowhere close to what the user's prompt needed it to be. So to in order to capture that difference, we have this KL divergence term. So KL divergence is actually low when the two probability distributions are close enough, and it is high when they are far enough. Now pi RL is a probability distribution of our instruction fine tuned model, and pi SFT is a probability distribution of a supervised fine tuned model. Now um, yes, so this is our objective function. On the right hand side, we can see the PPO policy, PPO pseudocode that is being used to train this model. Coming to the dataset, being the dataset sizes and specifications, this is part of the slide deck which could be seen. There are the key results are something that is important to be stated here. After the instruction fine-tuned LLM, that is aligned LLM, aligned LLM, we are able to see that 85% of the labelers, that is the people who created the training data set, 85% of them are actually preferring the instruct GPT's responses rather than the GPT-3 responses, which were unfine tuned. Also, there was a set of people who were held out and they did not create the training data set, but they were included in validation of the data set. Among them also, 71% of them actually preferred the instruct GPT responses rather than GPT-3 responses. And the instruct GPT was able to produce 2 times more true answers than the GPT-3 model on a particular benchmark dataset. And most importantly, the instruct GPT has 100 times lesser parameters rather than GPT-3 model. Now this is a graph stating the win rate of our SFT baselines versus the original GPT. The outcomes of this paper, there are key results and drawbacks. Coming to the key results, we are able to see that uh, the size of the model doesn't matter much when it comes to understanding humans task, but a more aligned model is more preferred rather than a large size model, because GPT-3 has 175 billion parameters while InstructGPT is 100 times lesser number of parameters. The InstructGPT was able to generate helpful responses and ensuring that it is honest as well rather than simply hallucinating. InstructGPT was also able to generalize to other topics which are not included in the training dataset, as we saw in the 71% preferences of held out dataset on the held out dataset. Thus, InstructGPT is able to generalize, which was lacking in supervised fine tuning. But there are drawbacks of this model as well. The main drawback is multi-stage process. We have three stages, and all the three are sequential in nature. Thus, it is difficult and time-consuming. Not all the HS are served by this pipeline. We see that the the Instruct GPT is what not less harmless when compared to GPT-3. In fact, it produces more toxic output than GPT-3 when explicitly asked to state. And because of RL being used, the training is quite unstable. There is a term called as alignment tax that the paper uses, which is basically stating that there's a compromise of standard NLP task being done by the LLM when you fine tune it using RLHF, meaning that our LLM is actually our LLM actually hurts its performance in standard NLP benchmarks just because we want the LLM to be aligned towards humans' preferences, and this is the cost that the LLM has to pay in order to get it into alignment. And there are some failure modes as well for this for Instruct GPT as well, where well false premise acceptance, where we assume that the prompt is true. Not we, Instruct GPT assumes that the prompt is true, but that is not the case always. And again, uh, in order to be more polite and not very explicit, Instruct GPT starts thinking a lot for simple questions such as what would happen if you fire a cannonball on a pumpkin. So these are a few issues that Instruct GPT fails. However, it has learned to be better at the general or average case. There are broader implications of this alignment research of this paper for alignment research. First thing is alignment cost is quite low when compared to pre-training, uh, because it is not a very hefty pipeline. Second thing, as we said, that trained RLHF pipeline trained GPT is able to generalize beyond the training distribution, which is a good thing. Now, again, the third important thing that this paper does not address explicitly is that hiring people in order to ensure that we train a particular model is not equivalent to generalizing the model for the entire humanity because of cultural differences and multiple things, so that has to be taken care still. And RLHF model is not a safe solution on its own, because as explicitly stated in the paper, that these models are not fully safe and nor fully aligned. So there is a lot of work to be done yet, but this can serve as a proper baseline to this problem. Uh, so finally, we see that the problem next token prediction is not equivalent to helpfulness. So large language models were not able to be helpful for particular tasks where and understand user intent. The solution was RLHF. Using RLHF in three steps: the supervised fine tuning, reward modeling, and PPO with KL penalty. Um, the result was that smaller size models are able to outperform larger size models when it comes to human preferences. But the issue is that bias and misuse still remain, and there's no safety guarantee. Let's do a real life testing of our responses. Now, where is it? Real time testing. We asked Instruct GPT to explain black holes to 7-year old in three sentences. The response that it generated was as follows: a black hole is a really massive thing that sucks in and traps everything, anything nearby. So basically, it is explaining by giving examples that the user, that a 7-year kid would know about a small, non-technical ways of explaining it. However, if we look at asking GPT-3 about the same thing, it is bringing terms such as gravity and space, stars and dust, which a 7-year kid might not know. So yes, this is it. There are other the limitations of this methodology is mostly served by a method called as DPO, which will be covered in the next paper. Thank you.